Welcome to the deep dive. Okay, so you've handed us this great set of sources, articles, some research papers, even your notes all digging into quantum computing. It feels, well, futuristic, doesn't it?
It really does. Very sci-fi.
But it's becoming real fast. So we're going to try and unpack this material together, get a handle on what this revolution really is, how it works fundamentally, and maybe what it means for, the future you're keeping an eye on.
It's definitely a fascinating area, complex for sure, but the sources you've gathered give a pretty good overview of the core ideas and, importantly, where it's heading and the big implications.
Great, let's dive in then. Since you follow this, we're moving beyond the basic bits in, say, your phone or laptop. Those are always just a 0 or 1, right? Definite states.
Exactly. But here, the basic unit is the quantum bit, or qubit. And it plays by different rules entirely, quantum mechanical rules.
Okay, so what are these rules? How does a qubit work?
Well, the first key principle is superposition. Think of it like this. A normal bit has to be either 0 or 1. A qubit, though, it can be 0, it can be 1, or, crucially, it can be in a combination of both states at the very same time.
Both at once. So it's like exploring multiple possibilities simultaneously.
Precisely. That's where a lot of the potential computing power comes from. It opens up a whole new space for calculations.
Okay, superposition.
Yeah.
What else makes these qubits special? What other quantum weirdness is involved?
Right. The next big one is entanglement. This is, well, it's pretty counterintuitive. You can link 2 or more qubits together so they share the same destiny, essentially.
Linked how?
Linked in a quantum way. If you measure the state of one entangled qubit, say you find it's a 0, you instantly know the state of the other one, no matter how far apart they are. Miles, even theoretically light years.
Whoa. Okay, that is weird. Spooky, as Einstein supposedly called it.
Yeah, spooky action at a distance. But it's real, and it's another resource quantum computers can actually use in algorithms. This correlation is powerful.
So you have superposition, entanglement. How do you actually get a reliable answer out of all this, probabilistic weirdness?
That involves quantum interference. Basically, quantum algorithms are cleverly designed so that the computational pathways leading to the wrong answers cancel each other out. That's destructive interference.
Okay.
And the pathways leading to the right answer reinforce each other. That's constructive interference.
Yeah.
It sort of steers the quantum state towards the solution you want. It's like probability engineering.
So you're not using standard logic gates like AND or not that flip bits. It's something else.
Exactly. Quantum computers use quantum gates. These gates manipulate the qubits, maybe putting them into superposition, entangling them, or rotating their state in that combined 0 and 1 space. They perform quantum operations.
Got it. And these operations are the heart of the computation.
They are. But, and this is a huge but, these quantum states are incredibly fragile, like ridiculously sensitive. Any little vibration, tiny temperature change, a stray bit of light or electromagnetic field, it can all knock the qubit out of its quantum state. It's called decoherence. So keeping them stable long enough to actually do a calculation is a massive engineering challenge.
Which explains why they need those extreme conditions we hear about.
Yep. Often near absolute 0 temperatures, shielded like crazy from any outside interference or noise. It's complex stuff.
Okay, makes sense why we don't have them on our desks. Not yet, anyway. These ideas must have built on earlier physics, right? They didn't just pop up.
Oh, absolutely not.
Yeah.
The groundwork goes way back to the early 20th century. People like Max Planck, Albert Einstein, Bohr, Schrödinger, they were the ones figuring out the fundamental rules of quantum mechanics itself.
The really basic science.
Right. Trying to understand how matter and energy behave at the tiniest scales, which is, deeply weird and non-intuitive compared to our everyday world. That understanding was the essential first step.
But the actual idea of using quantum mechanics for computing,
Yeah.
that came later, sometime in the 80s, based on the notes.
Yeah, that's right. It was physicists like Richard Feynman and David Deutsch who started thinking, hey, the universe runs on quantum rules. What if we build a computer that also runs on quantum rules? Feynman famously suggested that to simulate quantum systems efficiently, you'd probably need a quantum computer.
Using quantum to simulate quantum makes sense.
Deutsch formalized the idea of a universal quantum computer.
Well,
They saw the potential power, especially for certain kinds of problems.
and then came the moment that really woke people up to the practical implications. Peter Shor's algorithm.
Absolutely. 1994, that was huge.
Wow.
Shor showed, theoretically, that a quantum computer could factor large numbers exponentially faster than any classical computer possibly could.
And factoring large numbers is the basis for a lot of current encryption, right?
Exactly. Things like RSA encryption, which protects a lot of online data, relies on the fact that it's incredibly hard for classical computers to factor the large numbers used in the keys. Shor's algorithm basically showed a quantum computer could break that kind of encryption. That really put quantum computing on the map for governments and security agencies.
A potential code breaker. Okay. Fast forward a bit then to something more recent that you probably tracked Google's big announcement in 2019.
Yes, quantum supremacy. Google claimed their Sycamore processor performed a specific, very particular mathematical task in about 200 seconds.
Okay.
And they estimated that the same task would take the world's most powerful classical supercomputer, Summit at the time, something like 10,000 years.
Wow. So a massive speed up, even if the task itself wasn't immediately useful.
Precisely. There was debate about the exact numbers and the term supremacy, but the core point was demonstrating experimentally that a quantum device could, for at least one specific problem, vastly outperform any existing classical computer. It was a proof of concept milestone.
Okay, so let's really nail down this difference. Classical computers work sequentially, one step after another. Quantum computers, because of superposition, can kind of explore many paths at once.
That's the essence of it. The parallelism isn't like having many processors working side by side in a classical supercomputer. It's a fundamentally different kind, exploiting that quantum ability to be in multiple states simultaneously. It gives them an advantage for certain problem structures.
So they're not just universally faster, they're better at specific types of problems.
Exactly right. They won't replace your laptop for writing emails or browsing the web. Classical computers are great for that. But quantum computers excel, where classical ones hit a wall, especially with problems involving huge numbers of possibilities or complex interactions.
Like what, for example?
Well, optimization problems are a big one, finding the best solution out of a vast search space. Simulating quantum systems themselves, which is intrinsically hard for classical machines. And, as we mentioned, cryptography.
You mentioned simulating quantum systems. The sources highlighted simulating molecules.
Yes, that's a perfect example. Trying to accurately simulate the quantum mechanical behavior of even a moderately complex molecule, like a potential new drug interacting with a protein. The complexity just explodes for a classical computer. It becomes computationally intractable, basically impossible.
Well, for a quantum computer.
It's still hard, but it's a problem that maps much more naturally onto how a quantum computer works. Simulating quantum mechanics with quantum mechanics. This could revolutionize materials, science, and drug discovery. It's a capability leap.
Okay, this is where it gets really exciting for you, following the applications.
Yeah.
Based on the sources, what are the key areas where this unique power could actually make a difference?
Well, we've touched on cryptography and security already. It's a double-edged sword, right? Threatens current encryption.
Like RSA.
Yeah. But it also drives the development of new quantum-safe encryption methods. So breaking codes on one hand, creating new secure methods on the other. It's a major focus.
Makes sense. What about in medicine or healthcare? You mentioned drug discovery.
Exactly. Simulating how molecules interact could massively speed up the process of finding and testing new drugs. Instead of slow, expensive lab work for every possibility, you could model interactions computationally first. It could also help with personalized medicine, analyzing complex genetic data much faster. Huge potential there.
And how does it link up with AI and machine learning? That field's already moving so fast.
Quantum could give AI another boost. Some quantum algorithms might dramatically speed up the training of complex machine learning models, which can take weeks or months classically. It could also help AI tackle really complex pattern recognition or optimization tasks that are currently bottlenecks, finding correlations in enormous data sets, for instance.
Right. And finance. Always looking for an edge there.
Oh, definitely. Financial modeling is another area. Think about optimizing investment portfolios. Quantum algorithms might handle far more complex scenarios and variables than current methods. Risk analysis, fraud detection by spotting subtle patterns in transaction data. These are all areas being actively explored.
It's not just theoretical then. Are companies actually trying this stuff out?
Yes. The sources mentioned some early examples. DHL, the logistics company, apparently explored using quantum approaches to optimize delivery routes, a classic, really hard optimization problem.
Finding the best way to deliver millions of packages.
Exactly. And Volkswagen was mentioned too, using it for supply chain optimization. These are early pilot projects, but it shows that big companies are starting to see potential practical value, even with today's limited quantum hardware.
And even really big picture challenges like climate modeling.
That's another potential application. Simulating the Earth's climate is incredibly complex atmosphere, oceans, ice, land interacting. Quantum computers might, down the line, allow for much more detailed and accurate climate models, improving our understanding and prediction of climate change, and even maybe things like long-range weather forecasting.
So, potential everywhere. But where are we today? Who are the main companies or groups actually building these things?
It's becoming a pretty active landscape. You've got the big tech players, obviously, Google with their Sycamore chip and ongoing research. IBM has been very prominent, especially with their IBM Quantum Experience, making their machines accessible over the cloud for people to experiment with.
So you can actually run code on a real quantum computer.
Yeah, small stuff, but yes.
Yep.
Microsoft has its Azure Quantum Platform, which is more of an ecosystem approach, integrating hardware from different partners.
Yeah.
And then there are important startups like Rigetti Computing, IonQ, Sequantum,
Yeah.
each often pursuing slightly different physical ways of making qubits.
Different technologies for the qubits themselves.
Right. Superconducting circuits like Google and IBM use, trapped ions like IonQ, photonics. There isn't one winning approach yet. And beyond companies, governments are pouring money into this.
The sources mention significant investment, global hubs emerging.
Absolutely. Billions are flowing in from governments and venture capital. It's seen as strategically vital technology now. You see major hubs developing in the US, China, Germany, Canada, the UK. There's a real global push and a bit of a race for talent and breakthroughs.
But it can't be smooth sailing. What are the major hurdles, the big challenges holding things back right now?
Oh, there are huge challenges. Scalability is probably the biggest one. Current systems have, dozens, maybe hundreds of qubits. Useful fault-tolerant quantum computers will likely need thousands, maybe millions, of high-quality interconnected qubits. Getting there is incredibly hard.
Just building bigger systems that work reliably.
Exactly. And tied to that is error correction. As we said, qubits are super fragile, prone to errors from noise decoherence.
Right.
So you need sophisticated methods to constantly check for and fix these errors without destroying the quantum computation itself. That's a massive theoretical and engineering problem. Many more physical qubits are needed just for the error correction overhead than for the actual calculation.
So you need way more qubits than just the ones doing the math.
Yeah, potentially thousands of physical qubits to make one reliable logical qubit. And then there's simply the cost. Building and maintaining these machines with the cryogenics and shielding and specialized components, it's incredibly expensive.
Okay, scale, errors, cost, big hurdles. But looking ahead, what's the outlook? The sources mention some pretty big market projections.
Yeah, the numbers are getting large, although it's still early days. One projection mentioned was, $125 billion market by 2030? That seems ambitious, but it reflects the expectation that the technology will mature and start finding real commercial applications across various industries.
And that implies a shift in needed skills, too.
For sure. There's going to be growing demand for people who understand quantum information science, who can develop quantum algorithms, who can operate and maintain the hardware. A whole new set of expertise will be needed.
And given the power, especially for code breaking and potentially simulation, there's that geopolitical angle too, isn't there? The race you mentioned.
Definitely. National security implications are huge. Being ahead in quantum could offer advantages in intelligence gathering, breaking adversaries' codes, developing new materials for defense, secure communications. So yeah, there's absolutely a global race for quantum dominance, driving a lot of the investment and urgency.
So summing up the current state, we're past pure theory. Machines exist, but they're still kind of small and error-prone.
That's a good way to put it. We're often said to be in the NISQ era, noisy intermediate-scale quantum. The machines are getting big enough to do things classical computers can't, maybe, but they're noisy, error-prone, and not yet fault-tolerant.
So still a way to go before they're solving major commercial problems routinely.
Long way, most likely. And it's important to remember they probably won't replace classical computers entirely. The vision is more of a hybrid approach for classical computers handling most tasks, but handing off specific, really hard calculations to a quantum coprocessor or accelerator. Integration will be key.
Okay, thinking about that future, that power, this is where it gets really interesting for you, the listener. What are the bigger societal questions or ethical points the sources bring up?
Well, the security risk is probably the most immediate and concrete one discussed. The threat to existing encryption is real, even if it's years away for widespread impact.
So everything from bank transactions to government secrets could eventually be vulnerable.
Potentially, yes. Which is why there's such a push for developing and standardizing quantum-resistant cryptography now before large-scale quantum computers arrive. Governments, banks, critical infrastructure, They all need to start planning that transition. It's a huge undertaking.
What about access? If these things are so expensive and complex?
That's another major concern highlighted. Will this incredible power be concentrated in the hands of a few wealthy nations or large corporations? Could it actually worsen the digital divide, creating quantum haves and have-nots? Ensuring broad access to the benefits is a real challenge.
So it's not just about can we build it, but should we, and how do we manage it?
Exactly.
Yeah.
There are broader ethical questions. How should society govern this technology? Who owns the breakthroughs, especially when they might have come from publicly funded research? How do we anticipate and mitigate potential misuse? These are questions we need to start asking now, not after the fact.
Yeah, those are definitely the kinds of things that make you stop and think beyond just the amazing science. It really grounds it.
It's an incredibly powerful technology in the making. The potential benefits are enormous, but so are the challenges, technical, economic, and societal. It demands careful thought and planning.
Well, thank you for walking through this with us, really digging into these sources on quantum computing. It's clear this is something that's going to, ripple outwards in lots of ways.
Absolutely. It's been fascinating to discuss.
So as you, our listener, reflect on all this, here's maybe a final thought sparked by those sources. We've talked about how quantum computing could solve problems that are just impossible today, designing life-saving drugs, maybe understanding climate change fully. But we also heard about the immense cost, the complexity, the potential for unequal access. So what does that tension mean for how progress happens globally? If the keys to solving humanity's biggest challenges are held only by a few, how do we ensure those solutions actually benefit everyone? How do we navigate that? Something to chew on. Until the next deep dive, keep exploring.